Well, good morning, everyone. How are we doing? Good? All right. Studied what we went over the last time on Monday, right? Yes, we practiced it and studied it, because otherwise we'll forget things, right? If we don't study every day. Yeah, so we need to make sure we're finding that time in our schedule to study every day and practice doing the homework, right? Okay, and we left off talking about how to calculate this. Do you remember? Okay, and we need to remember that formula, don't we? Because is it going to be provided to us? No. All right, so make sure that you do remember that and be able to calculate that. So I hope you were able to practice that the other day after class. Okay, so we've talked about so far some information that's tied to the periodic table, didn't we? We said, oh yeah, we know what those numbers are above it. What do we call these numbers again? They're called the what? Atomic number. Very good. And then we talked about the number underneath the symbols, that number over here, the decimals. What was that? Atomic mass or atomic weight, right? And that's what we calculated as the average weight. Like put the whole atom on the balance and it's like, oh, this is how much it weighs, right? Okay, well, we're going to tie more and more things to the periodic table as we go. You'll be able to tell me stuff like, hey, which is bigger, which is smaller, and which is more electronegative, and electron affinity, and all those things, and even configuration. So we're going to tie as much as we can to the periodic table. So now we have to start talking about, well, how is the periodic table put together? I mean, how did that happen? Well, the Mendeleev put this together for us, and what happened is if you take all the elements and you line them up by atomic number, like count them out, 1, 2, 3, 4, all the way, and then we start looking at the physical properties and chemical properties, and we're like, oh, look, here's an inert gas. And then right next to it is a soft reactive metal. Interesting. So we keep going, and we're looking at the properties, and we're like, whoa, look, there's another inert gas. And next to it is another soft reactive metal. And we keep looking at properties, and we're like, what, again? Another inert gas next to a soft reactive metal? Wow! The properties are periodically repeating, aren't they? Do we see how they periodically repeat? So hence the name periodic table. So what we're going to do is we're going to take those elements that have similar chemical and physical properties and we're going to stack them all up into a column. And that's how we have the periodic table. So we've grouped them by column. And in these columns, we're going to have similar what? What did we say? Similar what? Properties. What kind of properties? Physical and chemical. You can remember both of these? Okay, it's chemical and physical. Sometimes we get confused and think it's one or the other, but it is both of those, chemical and physical properties, are in these columns. Okay, not rows, because when we set up the periodic table, we'll see we have groups and columns. All right, so we talked about the columns. What do we call the columns, actually? Elements have families just like people. Sodium reminds me of my mom, bitter and reactive. Okay? So what are we calling those columns then? We're calling them families. Actually, that's what we're calling them, is families. Why are we calling them families?
What is the one for toxic?
Oh, does what make sense in it? Yeah. Yeah, it cuts off a little bit. Because they're listed in them all. So why would you call them families? Because they're related, similar, right? Because in your family, don't you kind of physically look sort of alike? Sometimes we behave alike, right? Yeah, some of them are like, no, not my family, but some of us are all right. Okay, so that's why we're calling them families. Similar physical and chemical properties. Not only do we call them families, but we're also going to call them groups. Okay, so if I say a group, you're going to think up and down column. Okay, so don't confuse that with a row. A row is what we call a period. So if I say period, I'm talking about a row. If I say group or family, it's an up and down column. Periods do not have similar chemical and physical properties. Only the groups do. Now, if we took the periodic table and we lined it all up by the groups, you see that we are arranged in periods as well as groups. Now, look at this one and look at our current periodic table. What's changed? What's different? It's arranged differently in what way?
Like it's flatter and skinnier.
It's flatter and skinnier. Yeah, we cut something out of the middle. Yeah, we cut this out of the middle. We moved it down and slid the 2 over. Right? So it fits now nicely on a page, right? Not so skinny. Okay, so that's the way it is. So when you're watching the numbers and you're looking at the periodic table and we're going through the numbers, be careful about the way it looks. This is where we have 56, and then it goes to 71. It's like, well, where are all the other ones? You have to go down and follow them in order, okay? All right, so you see that? So we pulled it down and put it through here. Now, there is some differences between element 57 and 89. Okay, this is the lanthanides. Those are the actinides. In some periodic table, this one is going to be down here. In other periodic tables, it's going to be up here. Like, for example, this is 57 is down here. Look where 57 is on that periodic table. Is it down below or is it up in the transitions? It's up in the transitions. Yeah, there's some differences in the way periodic tables are. And you're thinking, well, why is there a difference? Well, one of them emphasizes similar chemical and physical properties. Another one emphasizes the configuration a little bit more. Okay, we'll address that more in chapter 6, but I just kind of want to point it out to you right now. The one that we have when we take the exam is the one where lanthanide and actinide are up in the transition metals. Okay, just a little difference there. All right, so here's our current periodic table. And the periods is what we called the rows, right? And the columns we called what? Families or groups. Okay, very good. Now, we notice that the A's are on the outside and the B's are in the middle. Do you notice that? The A columns are on the outside and the B columns are in the middle. Okay, well, we call the A column something and the B column something else, and we'll go over that in just a minute. But in some countries, the A and B columns are switched. So to avoid that confusion, IUPAC, that's the International Union of Pure and Applied Chemistry, said, hey, we're going to number them 1 through 18. Okay, so it's all clear. 1 through 18, everybody. Now, the A on the outside and B in the middle, that's the North American system. So since we're in the North American area, we will go with the A's on the outside, B's in the middle. Okay, an alternative would be 1 through 18 as well. Now, we need to know the names and all that stuff about the periodic table. So I think you guys pretty much know that. So I've got this handout that I wanted to see if you know what they are. So there are the questions, there are the words. I want you to write in the names of each of those columns. Okay, so I'll give you about 5 minutes to do that. If you don't know this, then check with your neighbor or get up and move around the room and find somebody who knows this. Okay, we only have about 5 minutes, so you're going to have to move quickly. So put what you know and find somebody who knows the other ones that you don't. Okay? Okay, so we do need to know all these. We do need to know all the names and all the answers to these questions. So make sure that you do keep this around with you to study. But fill it in, see what you know. And the words you had to choose from are these over here on the side. It's one of those. Oh yeah, you can look in your textbook if you've answered all you can. Flip open your textbook. You can take a look at that periodic table there. See how much you know. See, maybe it's listed. Here's some information. Some of that information should be just on the inside cover of your periodic table. Do you have periodic table on the inside front cover?
Yes.
Yeah, there you go. some information right across there. Okay, so if you have your textbook and you look in the inside front cover with the periodic table, you should be able to find that. Okay, so ask around somebody who may know that if you don't know it. And if you know it, share it with the people around you. Okay, so if you know it, share it. If you don't know it, ask someone. Okay, looks like some of us have got it. Some of us are almost there. Okay, if you have it, look around you and share with what you know with the people around you. Okay, so check with somebody. If you need to, get up and walk around. Find somebody who's got it all filled in. Okay, fill it in. Put the names of the columns as well. Okay, if you need to, process of elimination. Okay, have you almost got the names of these columns? Don't forget to write in the names of the columns at the top there. Okay, ask somebody if you don't know. Okay, don't forget the names across the top. Okay, so write those names across the top there. Put what you know, look it up, talk to somebody. Yes, the whole row. The column, rather, the whole column. Great, thanks.
And for this one,
All right, so we about wrapped up. Has everybody got it? You think you got it?
Yeah, almost.
Yeah, that's when that one goes. Oh, yeah, okay. Process of elimination there. It's the only name left. All right. Okay, whew, did we get it?
Yeah.
All right, so you do need to know all these things on there. Start with the group names. What's group 1A called? Alkali. Group 2A? Alkaline earth. It's alphabetical. That may be a way to remember it. Alkali comes before alkaline. What about group 6A? What are we calling that? Chalcogens. Yeah, it's spelled and pronounced a little differently. Chalcogens. Chalcogens. 7A is halogens. And 8A, noble gases. Do you see how column 8A is kind of like taller than all the rest? It's kind of like they're nobility. They're like noble gases. We're nobility and we stay in our tower. And we don't want to associate with any of the other elements on the periodic table because we have all that we want and we don't want to share. So in other words, we're saying the noble gases are very unreactive. Okay, they just like to be by themselves. They don't do any reacting. If they can help it, they would rather not. Now, meanwhile, all the other elements on the periodic table, they're like, oh, if I could be just like the noble gases, all my dreams would come true. So we'll talk about how all the other elements on the periodic table are going to try and be like the noble gases. Okay, so everybody else get the rest of that. Does it look like this? Yeah, did we get them? Okay, so if I'm saying, hey, we're going to talk about the charges of the main group elements, you need to know which ones I'm talking about. And if I say, oh, the halogen properties are this, you need to know which column I'm talking about. So this will be important for you to remember these things, to understand what it is that I'm saying. Make sense? Okay, metals and nonmetals, right? So mostly we are made up of going to be what? Metals are over here, right? Okay, and then the nonmetals over here. Now you know the properties of metals, right? What are some of the properties of metals? Okay, very good. What else? Think of a metal. Is it shiny? Yeah, okay. They have luster. They're shiny. Do they conduct anything? Yeah, what do you make your wires out of? Yeah, metal, copper wires. Okay. Okay, so they conduct electricity. They conduct heat. We say ductile because you can draw them into wires. We say malleable. It means you can form them. You know, think of aluminum foil, you know. Okay, so those are some of the properties of metals. The properties of the nonmetals are opposite of that, right? We don't conduct electricity, we're not malleable, we're not ductile. Okay, so now we have those that are in between, those elements that are in between the metals and the nonmetals along that black stair-step line. And those are called metalloids, right? Well, what are the properties do you think of metalloids? Okay. A little bit of both. Okay, so let's see. Metals conduct electricity, nonmetals don't. A little bit of both. What would that mean metalloids would do?
They might be the best at conducting.
Ah, okay. So, but they do conduct some, right?
Yeah.
Not as good as the metals, but more than the nonmetals. So they conduct some. They're sort of conductors. Magnet's a different thing. This is conducting electricity. So they conduct some electricity, right? Sort of conductors, you could say. How about semiconductors? Oh, have you heard that term? What's a semiconductor we use in the computers all the time? Computer industry, tech industry, we use what? Yeah, what else? How about silicon? Yeah, have you heard about that? Okay, silicon. Silicon, is that a semiconductor? Yeah, it's a metalloid, isn't it? So all this time, semiconductor's been part of your everyday usage or language, and you didn't know really what that was. Well, now you know it's a metalloid, and it has properties in between a metal and a nonmetal. Okay, let's take a look at all these. Are all these, let's go back to elements and compounds, are all of these compounds? What do you think? Are they all compounds?
Yeah.
Okay. All of them? Look a little bit closer. Is there one that's not? It's oxygen. Okay, so everybody see the difference? Are these all compounds? No. One of them is an element, and that is oxygen. Another question. Are these all molecules? Yes. Do you remember the difference between compounds and molecules? Okay, these are not all compounds. Oxygen is not a compound. However, these are all molecules, aren't they? Okay, do you remember the definition of a molecule we said was what? What's the definition of a molecule? More than one what? Two or more than atoms. Very good. We want to know that. We got to make sure we study this. Two or more atoms. What's our definition of a compound? Two or more elements, right? In constant composition, right? Okay, very good. So this is going to be a molecule of an element. Molecule of an element. Now we give this particular type of element that exists in its natural state under room conditions, kind of like where we are right now, as a molecule. We call that a diatomic element. Di, how many is di? Two. So does it make sense why it's a diatomic element, 2 atoms? Oxygen is one of those elements that says, you know what, I really want to have a buddy. Okay, if I can't find somebody, then I'm going to pair up with one another oxygen. Okay, so that's why this is a diatomic. Now notice it is not a diatomic when it's in a compound. Is that going to be a diatomic? No, because it's already with somebody. Okay, it's when it's by itself. All right, when it's by itself that it pairs up like that. Or if it's not an anion. Okay, if an anion, then it's got some electrons. Does that make sense? And when it's a diatomic? Okay, now there are 7 diatomics. You have to know all 7. Okay, 7 diatomics. All right, so we know the difference between elements and compounds. 7 diatomics. Okay, you can remember that it's 7, and it starts with the element 7. What's this element 7? Nitrogen. Does everybody see that? Okay, element 7 is nitrogen. So it starts with that. And there are 7, so we're going to count out 7. So we go nitrogen, oxygen, fluorine. And we're going to make the shape of a 7. We start with 7, make the shape of a 7. Let's count 7. Nitrogen, oxygen, fluorine. Now, does you think neon wants to be a diatomic? No. Remember, they don't want to. That's nobility. Right, so we're going to go down. Fluorine, chlorine, bromine, iodine. Here we don't know too much about these elements, so we stop here. But that's not 7. That's only 6. So where's the 7th one? Hydrogen is the 7th one. Exactly. Now, you guys know hydrogen is going to be a non-metal. Does everybody know that? Okay, hydrogen is a non-metal. Even though it appears sometimes on the left side of the periodic table, it is a non-metal. We try to show that by the color here or breaking it away from the metal side. It's not really touching. We try to show some things about that, okay? Different colors, even though it's on this side, and we'll learn later why it's on this metal side of the periodic table, but just want to make sure that we understand that it is a non-metal. Okay, so... No, it is not an alkali metal. It is a non-metal. It's not a metal. Okay? Even though it's over there, it's not a metal. It's not an alkali metal. Okay, and we'll learn later why. We're like, why is it over the metals if it's not an alkali metal? Well, we'll talk about it. It's got to do with its electron configurations. We haven't got there yet. Okay, so just want to make sure we understand that it's not an alkali metal. Yeah, all right, so... we were talking about the 7 diatomics, right? Okay, so starts with the number 7, forms a 7, and which one's the 7th one? Hydrogen. Yes, we do need to remember that. Okay, so forms a 7, hydrogen is the 7th one. Those are our diatomics. Now you do need to know these and memorize these. Another way that you can remember this is that you can go with horses, H, horses, need, N, oats, O, for, F, clear, Cl, brown, Br, eyes. Horses need oats for clear, brown, eyes. Okay, so that's another way to remember it. You can remember that there are 7, starts with 7, forms a 7, hydrogen is the 7th one. Or we can say horses need oats for clear, brown, eyes. Either one. You guys like the 7 thing, or do you like the horses thing? The horses thing? Okay. All right, either way you want to remember it. We do need to know those 7 diatomics. Okay, well, let's talk about, we've talked about compounds, right? Okay, well, some, in molecules, we talked about how compounds can be in a molecule. Okay, well, that makes sense. But some substances are not molecules. They are in crystalline structure. So this is a picture of sodium chloride. You guys know what sodium chloride is? NaCl, which is table salt, right? Have you guys ever sprinkled out table salt and took a look? Yeah? What's it look like? Little squares. That's like little teeny squares. So if you haven't done that, go home and sprinkle some salt out and take a look and see all the cute little squares there are. Okay, that's the way sodium chloride comes. It comes in a crystal. This is a crystalline structure. If you go into 1412, you'll talk more about crystals. That's the way it looks. Well, what's inside one of those crystals? Let's take a look at that. What's inside one of those crystals? This is what's inside. Sodium and chloride ions. Do we have molecules? We don't, do we? You said, oh, the formula was NaCl. Well, that's not a molecule, is it? It's part of this gigantic crystalline structure. So there's lots of sodiums, lots of chlorides. It just alternates. Sodium chloride, sodium chloride, sodium chloride, sodium chloride. We don't have a molecule. We have a crystalline structure. So we're like, wow, how am I going to write the chemical formula for this? I don't want to write sodium a billion and chlorine a billion. I mean, what am I going to write here? I'm going to write the simplest ratio. So if there's an equal number of sodium and an equal number of chlorides, then what's the simplest ratio then? 1 to 1. That's why we write sodium chloride. And we call that simplest ratio a formula unit. So a formula unit is the simplest ratio. It's not a molecule of sodium chloride. It's a part of a crystal structure. But we're going to call that simplest ratio a formula unit. So ionic compounds have formula units. All right, does that make sense? Has everybody got that? Now, this formula unit we said was the simplest ratio. So we're going to call that something else. We're going to call that empirical formula. We're going to use that a lot in Chapter 3. It's an empirical formula. So what did we say an empirical formula was?
The simplest ratio.
Simplest ratio. Okay. Simplest ratio is an empirical formula. So ionic compounds then have empirical formulas. Make sense? Ionic compounds will be empirical formulas. We write them as empirical formulas. Okay, now next question. How do you know if it's an ionic compound or a molecular compound? We got to know that too. So how do we know that? Well, ionic compounds are made up of cations and anions. Remember how we talked about cations as a positive ion and anions are a negative ion? Okay, so what we say then is an ionic compound is made up of cations and anions. Now, another general rule of thumb that we'll have is that metals tend to form cations. And non-metals then would tend to form what? Anions. Right, that's going to be kind of one of our important rules of thumb.
So metals form
Cations.
cations.
Okay, so has everybody got that? Metals form cations. Are cations positive or negative? Positive. Very good. Metals form cations, and anions tend to be the what? Non-metals, right? So the non-metals tend to form anions. You know, that's a general rule of thumb.
What would a metalloid actually be?
That's a good question. What about metalloids? Well, metalloids are one of those that can be like, it can be either one, different. So when we go into naming ionic compounds, we will have to discern whether it's ionic or molecular. So what we're going to say is, along that stair-step line, if the metalloid is below the line, we're going to treat it as a metal. If that metalloid is above the line, we're going to treat that as a non-metal. Okay, we're just going to go with that general rule of thumb. I mean, it's a general rule of thumb. All right, so then we can say an ionic compound will consist of cations and anions. Another way to say that is an ionic compound will be between A metal and a nonmetal. Very good. Okay, so that's a good general rule of thumb. And there's always exceptions, but as mostly general rule of thumb. So an ionic compound is made up of what did we say? Cation anions, or we could say metals and nonmetals. Okay, so ionic compounds usually consist of metals and nonmetals. Well, what about molecular compounds then? Molecular compounds consist of nonmetals. There are no metals in a molecular compound. We're going to say that molecular compounds generally consist of, what did we say? Nonmetals. Exactly. Now, it's important for us to distinguish between molecular and ionic compound, because when we start naming these, we're going to have to know, because molecular compounds follow one set of rules, ionic compounds follow another. So the first thing you got to decide is it metal, is it molecular, or is it ionic? So we need to know the difference. Now, you're going to have to keep your periodic table out handy and look at that black stair-step line, because you may not be familiar with all these elements. You haven't maybe memorized their location. So you may not know where antimony is. You may not know, is that a metal or not metal? So you might need to keep that table handy and look to see. All right, so I want you to go through and I want you to put an M right there on your PowerPoints. Put an M by molecular or an I by ionic. Okay, so go through, think about it, write that down.
Staircase is non-metal, below staircase is metal.
Mm-hmm. Okay, how we coming? We got it? Okay, so I'm going to number you off, and I'm going to sign these out, and you can tell the class what you think it is. So I'm going to number them off, and then you check with your neighbor before you tell the class. Make sure you're right, okay? So we'll start with you. You'll be Jessica 1, 2, 3, 4, 5, 6, 7, 8. Caitlin, back to you. 9, 10, 11, 12, 13, 14, 15, and 16. And you guys are like, whew, that's okay, we'll get you next time. Okay. All right, so check with your neighbor, make sure you got them right, and then you can tell the class what you decided.
You know Sakina?
Yes, yes. Are you Sakina's friend? I thought that was you. I was like, oh, I don't know.
Yesterday I was telling her that we were both studying the polyatomic ionic. She's like, oh, I have flashcards. I was like, oh, yeah, they made them, so she gave them to me to study them. I was like, good.
Oh, good. Oh, good. Oh, good. Yeah, I wondered. I thought you looked familiar, and I thought, oh, maybe you're Sakina's friend. I keep wanting to call her Gentle, but it's Sakina. Well, good, good, good. Glad you got in. Glad you got in. Yeah, flashcard. Awesome. She's right. Flashcards. Okay, did we get them all right? You guys ready to tell the class what you got? Okay, so say it out loud so we can all hear clearly. Okay, number 1. Molecular. 2. Ionic. 3. Molecular. 4. Ionic. 5. Ionic. 6. Ionic. 7. Ionic. Oh, I know we think of, that's why hydrogen. We keep thinking it's a non-metal. I mean, it's a metal because it's over there on the metal side, right? But actually, it's a non-metal, isn't it? Okay, so hydrogen and chlorine, that's going to be what? Molecular. Yeah, it's going to be molecular. I know hydrogen was a tricky one. That was a tricky one. Yeah, hydrogen's going to be non-metal. Chlorine's going to be a non-metal. So this is molecular. Is that okay? All right, how about number 8? Molecular. 9.
Ionic.
Good. Ionic. 10. Molecular. Good. 11. Ionic. Good. 12. Ionic. Ooh, that's another tricky one. Okay, we'll come back to this one. 13. Molecular. Good. 14. Molecular. 15. Molecular. And 16. Okay, very good. Woo! Yay! We got that! We got that! Good job! Good job! Okay, well, let's go back. I know we had a couple tricky ones in here. This one with hydrogen. Another one with the barium and the sulfate. Okay, wow, that's got lots of elements, right, doesn't it? Okay, so the barium, that's the metal. And the sulfur and the oxygen, those are the nonmetals, right? But the sulfur and the oxygen, you guys recognize this as those polyatomic ions? Remember, we're supposed to be memorizing those? That's a polyatomic ion. What's it called? Sulfate. Do you know that? And what's its charge? -2. Okay, we have to know that. We should already be working on those. We should already be knowing that. Okay, so you have to know that because you're going to be able to understand our language, and we're talking about problems, and these polyatomic ions will really be a problem if you don't know them. You must know them. You remember that list? Okay, so hopefully we're all working on those flashcards. You've already got to have them down by now. We really, really need to do that. So this is a polyatomic ion. Okay, barium, is barium a polyatomic ion? No, it's just a barium ion. And this is sulfate. Sulfate polyatomic ion is made of sulfur and oxygens. So what's happening, this is like sulfur, like I'm sulfur. And I have 4 oxygens that are bonded to me. but we have extra electrons. That's why we're negatively charged. So we act as a group, okay? So sulfate's like, okay, all those oxygens are still bonded together, so we're going to move around like there's a reaction. Okay, so we're all going to go over here. This reaction, we're like, oh, wait, we all have to go over there. Okay, we act as a group, but we act as one ion. Make sense? Okay. Now, barium chloride, BaCl2, okay, that does not have a polyatomic ion, BaCl2. Barium is what we call a monatomic ion. It's just barium ion all by itself. And the chloride is also a monatomic ion all by itself. Now, there happens to be 2 chloride ions. It's just one chloride all by itself and another chloride all by itself. Okay, so they're still monatomic ions. Do we see the difference between a monatomic ion and a polyatomic ion? Because the chloride ion is just Cl minus. And the sulfite ion is SO4, 2 minus. So this acts as one ion. This acts as one ion. But this is only made up of one element. This is made up of lots of elements. So this is a monatomic ion, and this one's a polyatomic ion. Do you see the difference? Okay, so barium chloride is made up of completely monatomic ions. Barium sulfate is made up of a polyatomic ion and a monatomic ion. Okay, does everybody see that difference? All right. So make sure we know our polyatomic ions. Yay, polyatomic ions. We know those. All right. Well, we've been talking about types of formulas. We kind of already said, hey, there's molecular formulas. We understand molecular formulas, right? What that little subscript, we call that a subscript means. Okay, so you know what that this is a 2, you know what that subscript, that's called a subscript. We know what that means, right? What does that mean? That there are what? Two chloride ions? And how many bariums? Just 1. Okay, even though we don't see a 1 there, right? Okay, so that's called a subscript. That tells you the number of atoms. And that's a molecular formula. We've talked about molecules. And empirical formulas. Remember we said what kind of compounds have empirical formulas? For sure were the ionic, right? And we said, oh, that was the simplest ratio. The lowest whole number ratio, that's an empirical formula. So ionic compounds are empirical formulas. But what's interesting is that we can also have empirical formulas of a molecule. Okay, so let's put C6H12O6 here. Okay, this is a molecular or ionic compound? Molecular. So it comes in molecules, right? Okay, so this is an example of the molecule. This is it. This is the molecule right here. We often say it's called glucose. This is the molecule. Now, carbons are the black ones, oxygens are the red ones, hydrogens are the white ones. That's our molecule. Now, in that molecule, I can talk about a ratio. What would be the simplest ratio of this molecular compound? Okay, so here's our formula. So the simplest ratio would be 1 to 1. How'd you get that? Did you divide it out by 6? Yeah, that's what we call a empirical formula. CH2O. That's the simplest ratio in this molecule. Does it change the molecule, or is it still a molecule? It's still a molecule. All I'm saying is, hey, it's the simplest ratio in here. That's all I'm saying. So a molecular compound can have the simplest ratio, but an ionic compound, it is the simplest ratio, always. Okay, make sense? All right, for example, if we put up sodium chloride, NaCl, if this is the formula unit, what's the empirical formula? NaCl, right? It's already the simplest ratio, isn't it? Okay, how about lithium bromide? What's the simplest ratio? It's the same, LiBr, isn't it? Okay, does that make sense? Okay, how about, let's do some molecular compounds. Let's say H2O2. H2O2. What's the simplest ratio? H and O. Make sense? Okay, how about C2H2? What's the simplest ratio? CH. How about C6H6? What's the simplest ratio? CH. Whoa, you mean I can have different molecules that have the same empirical formula? Yes, I can. It doesn't mean that these are the same substance, not at all. It just means that within these molecules I do have the same empirical formula, the same ratio, but they're still two different compounds and two different molecules. Make sense? Okay, good. So now we know what empirical formulas are, because we're going to use empirical formulas for molecular compounds in Chapter 3. We also have a couple different ways that we can talk about these. First one we've already talked about, molecular formula. The next one is a structural formula. That's like, well, who's bonded to who? Because if you look at that molecular formula, C2H6O, we're like, well, who's bonded to who? I can't really tell. But when I draw it out in a structural formula, that helps me understand, oh, well, yeah, I can see where oxygen and who's bonded to the oxygen, right? Okay, that's a Lewis structure. We're going to draw Lewis structures at the end of the course, but we'll be working toward that. This is another way to represent that structure. We have the balls represent the atoms and the sticks represent the bonds. Okay, but when you put two atoms together, you're not going to have a little line in between them. So actually, this is a space-filling model. So these are just some representations. This is kind of more like what the actual molecule would look like. It's called a space-filling. So you'll see these. I just kind of want to show you those just so you can see what's coming up and recognize those as different models to represent our compounds and substances. All right, well, let's go back to talk about our ionic compounds. We said ionic compounds are defined between what? Metals and nonmetals. Okay, well, how do I know metals lose electrons, right? Okay, well, how do I know how many electrons metals want to lose? And what do nonmetals do? Gain electrons. Well, how do I know how many electrons the nonmetals want to gain? Like chlorine, for example. Wow, why is it going to gain 1? Why not 2? Why not 3? How am I supposed to know that? Well, let's think about this. Remember we said, oh, all the elements on the periodic table want to be like the noble gases. Oh, and their dreams will become true, right? Okay. Well, let's look at chlorine. See number 17 for chlorine? Where's the closest noble gas to chlorine? Yeah, 18, argon. Okay, well, how could chlorine be like argon? Can we ever change the atomic number? No. Okay, so chlorine's like, darn, can't do that. Well, what else could we do? Well, if we're neutral, remember the number of electrons equals the number of, what? Protons. That's neutral. So if argon has 18 protons, then argon will also have 18 electrons if we're neutral. And the electrons, we can change that all the time. So that's why chlorine's like, hey, I could be like the noble gas if I had 18 electrons, just like argon. So that's what chlorine wants to do, pick up 1 electron, because it has 17, right? And to get to 18, we would need to add 1 electron. So chlorine will add 1 electron. And that makes it have 18, like the nearest noble gas. And then we look at the charge and we're like, well, since we added 1 more electron, it's going to be a -1 charge because we got more electrons and protons, right? So chlorine will always be a -1 when it forms the anion. It's not going to be -2 or -3, it's going to be -1. Well, let's take a look at another element. Let's look at fluorine. This is in the halogen column. Fluorine. Where's the nearest noble gas to fluorine? Does everybody see neon? 10. And neon has 10 electrons, so what is fluorine going to do? It's going to add how many? 1. So what's its charge? -1. Okay, so fluorine's a -1 and chlorine's a -1. Makes sense. Let's try bromine. Where's the nearest noble gas to bromine? Krypton. Does everybody see 36 is krypton? Okay, well, if krypton has 36 electrons, what does bromine want to do? Add 1 more electron for what charge? -1 again? What do you think ion's going to be? Iodine's going to be? The same. Why is it going to be the same? It's in the same group. Remember that? We talked about groups and families. Okay, so in other words, we're saying all the halogens are going to have what charge? -1. So now we can look at the periodic table and we can start to assign charges to the main groups. And we will need to know those because we can't do ionic compounds without the charges. Okay, so all of group 7A is the halogens is going to have a charge of a -1. Well, let's talk about magnesium. Okay, magnesium, is that a metal or a non-metal? It's a metal, right? And metals tend to do what? Lose electrons. Okay, so let's look at magnesium. That's number 12 over here. So, what's the closest noble gas to magnesium? AR or neon? Which one is it? Neon is closer, because isn't 10 closer to 12 than 18? Yeah. So kind of got to go think the other way, don't we? So neon is the closest noble gas, and neon has 10 electrons when it's neutral. So what magnesium's like? Guys, I'd like to be like neon. What's it going to do? Lose how many? 2. So what's the charge of magnesium going to be? +2. Well, let's take a look at calcium. That's in the same column. What do you think calcium wants to do? Be like argon, so therefore it will lose 2 electrons. Again, 2 for a +2 charge? Wow. So do you think strontium is going to be a +2 and barium is a +2 in that same column? Yes. So in other words, group 2A, alkaline earth metals, group 2A has what charge? +2 charge. Does everybody see that? Now you know all that column is a +2 charge. Okay, well let's take a look at a different one. Let's take a look at sodium. Okay, what's the nearest noble gas to sodium? Neon, right. So sodium's going to have to do what? Lose 1. What's the charge of sodium? +1. What about potassium underneath that? What's the charge? 19, so it's going to be +1 again. How about rubidium and cesium? What are their charges going to be? +1, same thing. So all of group 1A is going to be +1. All right, so now do we start to see the pattern? Okay, you do need to know those. We do need to know those. I like those cat memes. I think they're so funny. Lost your electron? Got to keep an eye on them. Okay, so we see a pattern now. Group 1A is all going to be +1. Group 1A is +1. Group 2A is +2. Now these are monatomic ions, okay? Monatomic ions. Group 1A is +1. Group 2A is +2. Now these are main group. Now remember which one's the main group, so let's jump over to 3A. That's part of the main group. We're going to talking about the metals, so that's why it's underneath that line. So group 3A, we would say is +3. Group 4A doesn't really have a common ion. Okay, no common ion there. Group 5A, all right, well let's look at nitrogen. Nitrogen wants to be like the noble gas. So how many electrons do you think nitrogen has to have to be like neon, which is 10? Nitrogen has 7. What's nitrogen going to do? Gain 3. So this is a -3. What's the next column? What does oxygen want to do? It's one column closer. What's -2? And the halogens is even one column closer still, so they're going to be -1. Do you see the pattern? So it goes +1, +2, skip those, +3, column 4A is iffy, now we're switching over to negatives, then it counts down, -3, -2, -1. Does that make sense? Okay, so sulfur's going to be a -2, same thing. What about phosphorus? What do you think phosphide ion is going to be? Negative what? 3. Why'd you say -3? That's right, it's in that same column. Okay, make sense? Okay, so plus 1, plus 2, plus 3, iffy, minus 3, minus 2, minus 1. All right, make sense? Okay, you have to know those charges. Now, we skipped all the transition metals, and we also skipped the heavier, that means more atomic mass, heavier metals over here. Why are we skipping those? Because those do not really have only one charge. Like sodium's always plus 1. But in here, copper could be a plus 1, could be a plus 2. Iron, it could be plus 2, plus 3. How about tin? And lead, they could be plus 2, they could be plus 4. Okay, so this is what we call the charges vary in here. That's why we don't have a common ion there. It's not like the halogens or the chalcogens that have a set charge all the time. These are like, varies. Okay. Now that's why there are no specific charges. Now that we say that, there's always exceptions to the rule in chemistry. So we're like, okay, well, there is an exception, and it's the diagonal. Okay, so here's aluminum, and there's a little diagonal right here. What's this element called? This one, Ag is silver. This one is zinc, and this one is aluminum. Okay, we know aluminum is in 3A, right? So that's going to be a plus 3. And then you have this diagonal right here. Plus 3, you're going down. Plus 2, we're going down. Plus 1. So right here's your diagonal. 3, 2, 1. Okay, so memorize this also, because when I ask you what's the charge of zinc, you need to know that. What's the charge of silver? We're going to need to know that. Okay. Now there is another one underneath the zinc. That's cadmium. That behaves like zinc. It is a plus 2. You'll run across that once in a while. But not so with mercury. All right, so everybody got that little diagonal? It's your exception? Okay, questions about that? Okay, so what do we think? We got that? Is everybody okay with that? All right. So you want to check with your neighbor there and make sure you got all the right charges. Plus 1, plus 2, plus 3, iffy, minus 3, minus 2, minus 1, and then that little diagonal, right? Okay. All right, make sense? All right, well, let's talk about hydrogen. Remember we said, hydrogen, is hydrogen a metal or non-metal? It's a non-metal, right? Okay, well, great. If it's a non-metal, it can gain an electron, so it gains 1. Because it's trying to be like helium, right? So hydrogen will gain 1 electron to be a minus 1. But that's kind of interesting about hydrogen because we stuck it over on the left side in column 1A. Well, you know what? It can have the same charge as all of column 1A, even though it's not a metal. Again, we'll talk about electron configuration. So right now what we need to understand is that hydrogen is an interesting element. Woo, it could either be positive or negative. So it can be a plus 1 or it could be a minus 1. It can do both. In some periodic tables, they take hydrogen and they stick it right smack in the middle. Have you seen that? That's like, that's because it could either be a positive or a negative. So sometimes it does that. It's a little different from the other elements. Okay, make sense? Hydrogen can be a plus 1 or minus 1, but it is classified as a non-metal. Okay, make sense? We're good? So now you can tell me the charges. Like if I said to you, hey, what's the charge of bromine, the bromide ion, you would say what? Negative 1. Nitride? Negative 3. Sulfide? Negative 2. Strontium? Positive 2. Cesium? Positive 1. Zinc? Plus 2. Plus 2, right? Silver? Plus 1. Yay! Okay, good job. All right. Woo-woo! We know all those! Yay! Because we'll need to know those when we put together our ionic compounds. Because we can't put together the ionic compound correctly unless we know the charges. Ooh, yeah, we're going to get to that. All right, you know chemistry, we kind of build, right? All right, so we're building. We're going to get to that where we put those ionic compounds together. And we also need to name those ionic compounds. Okay, so before we name the ionic compounds, let's talk about naming them first pieces of it. Like an ionic compound was a cation and an anion. So let's practice, or we said metal and nonmetal. So let's practice naming the metal part first. All right, so if I said to you sodium ion, everybody can think of the charge, right? I mean, you know the charge. It's very specific. So all I have to do is say the name sodium, because we all look at the periodic table and we're like, oh yeah, sodium's always a +1. So that's all we have to say. If it only has one charge, then we say the name. So now let's go back to what we were talking about on the periodic table with the metals. Group 1A, that's a metal. They're all going to be, what, +1? So I say just the name. It doesn't matter how many of those ions I have. I only ever say the name. So I say lithium, or I say sodium, or I say potassium. Group 2A is the same. I can just say the name. And remember our little diagonal? Yeah. I could just say the name. Because if I said zinc ion, you guys automatically know, yeah, what that charge is, right? It's very clear. So with group 1A, group 2A, and the diagonal, just say the name. That's easy. Group 1A, group 2A, and the diagonal, just say the name of the metal. That's it. One possible charge, we just say the name. Well, what about the other metals? Well, they have more than one charge. So if I said, oh, the iron ion, does anything come to mind? Now you're like, well, that's not clear. Or if I said, oh, the lead ion, you're like, what? Okay, this doesn't mean anything to you. There's no meaning to that. So we need to be more specific, because those ions that we left blank can have more than one charge. Those metals can have more than one charge. They can be different ions. And when they're different ions, they can form different if they have different charges, they can form different substances. They're not the same. Okay, so if an element can have different charges, we're going to have to specify that. Because if an element has different charges, it will form different compounds and can behave differently. So now we need to be clear. Well, which ion are you talking about with the iron? Which ion are we talking about? So there's two ways that we can do this. So we can name these metals that have more than one charge in two different ways. The first way is the easiest. That's the Roman numeral method, and we'll do that one mostly, but we also need to know the ic and us ending as well. That's an older term. It's been around. We do need to know that. So let's talk about the Roman numeral first. If I say copper ion, and we're going to have be a +1, then how I would name that, I would just say it's copper. It's copper. So I spell it out, copper, parentheses, Roman numeral 1. The 1 means the charge. That's pretty clear, right? It's pretty straightforward. Okay, what about copper 2+? So I would write copper, and what would I put in Roman numeral? A 2. There you go. It is the charge. Okay, so let's do iron. Let's see, Fe2+. I would write iron what? Roman numeral 2. Okay, let's do another ion. Fe3+, I would write what? Iron, Roman numeral 3. There you go. That's how we do it. Now this is the charge, not how many ions there are. So let's take a look at this example. Iron 3. It's 3+. Iron 3 means the charge is 3. Look at the formula. Are there 3 irons in here? No. So that Roman numeral is not to say how many there are. It's to say what the charge is. Okay? All right, so for example, if we're talking about copper 1 chloride, we would write that CuCl. That's copper 1 chloride. Copper 2 chloride is CuCl2. Okay, again, that Roman numeral does not tell us the number of copper ions. It tells us the charge. Okay? Yeah? Woo, got that. Roman numerals, is that easy? Yeah, so if I say copper 2 ion, you're like, oh, I know the charge of that. If I said lead 4 ion, would you guys know the charge? Yeah, plus 4, right? Lead 2 ion would be what? Plus 2. Okay, good. Very good. Now let's talk about the ic and us endings. All right, the ic and us endings use some more Latin terms. Okay, so the only thing we can really say about the ic and us endings, if it ends in ic, then it is the higher charge. If it ends in us, it is the lower charge. And remember, maybe you can remember, higher has an I, ic has an I, so maybe you can remember those two go together. And lower has an O, and us has an O, so those two could go together. So when I'm looking at these copper 2 and copper 1, and I want to use that ending, I have to change the end of the word to one of these, and I'm going to use a lot of Latin terms. So for copper, we would use the Latin term. So plus 1, plus 2, which one is the plus 1? Is it the ic ending or the us ending? Us. So this becomes not copper us, cuprous. Cuprous. And then the higher one becomes cupric. Now let's do iron. So plus 2, is that an ic or an us ending? Us. It's an us. So I would call this ferrous. Yeah, a little bit of Latin there. And the us ending. And then this is the higher one, so this is called what? Ferric. Now, sometimes it's hard to know which one is the ic ending and which is the us ending if you don't know what these charges are. Okay, you do have to know both charges to know which is which. Notice that cuprous is a plus 1, but ferrous is a plus 2. So not all the us's are plus 1s. Not all the us's are plus 2s. Same thing. This is a cupric is a plus 2, yet this ferric is a plus 3. Some ic endings are plus 4. The only thing we can say is that if you have two charges, the higher one is the ic and the lower one is the us. So that means you're going to have to put these on flashcards, right? Oh, yay! I knew you'd be excited about that. All right, so these are some examples we were talking about. Cuprous, cupric, mercurous, and mercuric. Oh no, I thought we said one was higher and one was lower. Now there's mercurous and mercuric, and they both have the same charge, so now what? Anybody see any difference between mercurous and mercuric? Okay, so Hg is a symbol for mercury, and there's 2 of them, right? For mercurous. We're like, well, okay, let's write 2 of them out like this. And if the whole thing is plus 2, then couldn't I think about it? It's like, well, this could be a plus 1 and this could be a plus 1. Can I think of it that way? Okay, so maybe that would help you remember. Well, if that's the plus 1, then that must be the us ending. Okay, so that might maybe help you remember. Mercurous is Hg2, 2 plus. Mercurous is Hg2 plus. Chromus and chromic. Ferrous and ferric. And then a few more. Manganus, cobaltus, nickel, stannous, and plumbus. Okay, yeah, we're like, does anybody know what stannous is? That's, what element is that? Yeah, which one? Tin? Tin, yes, it is tin. Yeah, that one's tin. This one's lead. Okay. Now, which ic and us endings do we need to know? These are the ones. Okay, there are lots more, but this is like, I tried to pare down the list and just give you like the bare minimum that you need to know to be able to understand all the compounds and the elements we'll be talking about throughout the course. Okay, does that make sense? Now, you don't have to know the ic ones. If you want to, you can look it up and learn those as well. But these are the only ones that you really need to know, plus these. Is that all right? Does that make sense? Okay, so pare that list down. There's lots of others, but these are the ones that we need to know. So put these on flashcards. These are the ick endings. All right, so that's the metals. Now, remember, we only use a Roman numeral and ick ending if it has more than one charge. For example, group 1A. Are we going to use ick endings or Roman numeral with sodium?
No.
No. Are we going to use Roman numeral and ick ending with calcium? No. How about our diagonal with zinc? Are we going to use Roman numerals or ick endings with zinc? No. Okay, very good. It's just the ones that have more than one charge. All right, well, let's talk about naming the nonmetals, because we said, oh, ionic compounds are metals and nonmetals. So let's talk about naming the nonmetals. They simply end in "-ide". That's it. Okay, so oxygen would be what? Oxide. Fluorine would be fluoride. Nitrogen, nitride. Okay. Bromine, bromide. Sulfur, sulfide. Okay, we get that. How about hydrogen? Hydride. There you go. Ends in "-ide". Phew, that was easy. Oh, that doesn't form an anion. Yeah, so that would. These are for the ones that form our anions, right? Okay. Now, a large number of our anions are going to be those polyatomic ions. Yep, we need to know those polyatomic ions. Okay, a lot of them will be anions. There's really only two on that list that are the cations. Okay, the two that are on the cations, what are those? What? Hydronium and ammonium. You guys remember those? There's not very many. There's not very many cation polyatomic ions on your list. Okay, most of them are the anions. So if you look at that anion list, you'll see that most of them are anions, aren't they? Now, they're anions, so some of the polyatomic ions will end in "-ide". So, we've got some that are "-ide, like azide, hydroxide, cyanide. They're anions, they end in "-ide". Okay, but there are a lot of them that end in "-ate" or "-ite. Do you notice that? Yeah, and those have what does oxyanions mean to you? Oxyanions. Has an oxygen, and it's an anion. It's a polyatomic anion. So oxyanions mean polyatomic ions with oxygen. And those all have a lot of "-ates" and "-ites. Okay, so we do need to know those. So if you notice, we only have a few, hydronium and ammonium, that are positive. Here's your list that you need to know. There's a lot of these that have "-ate" and "-ite" endings, don't they? So we're going to try, I know it's a big list. You really, really need to start memorizing this list. But we're going to try and put a pattern to some of this list. So we can't put a pattern to everything, but if we put a pattern to some of it, it will help cut down on the memorizing that you have to do. Okay? And we're going to try and tie these polyatomic ions to the periodic table. That can help you. Okay, so one of the first patterns, and look at all the "-ates" and "-ites. There's a lot of "-ates" and "-ites. Well, this is the pattern. What's the difference between nitrate and nitrite? What's 2 and 3? Oxygens. So you're saying that the difference between the "-ate" and the "-ite is one oxygen? Yes. Did the charge change? No, it didn't. Nitrogen stays the same, the charge stays the same. The only thing that changes between the "-ate" ending and the "-ite ending is how many oxygens? 1. Well, if you know what nitrate is, if you know it's NO3, can't you figure out that nitrite is NO2? Yeah, okay, so now if you remember that rule, you've just cut down the number of these in half. Because if you know the "-ates, you already know the "-ites. So that's half as many there, right there. So let's go through and see if you can tell me. So I've got 4 and 3. So one of those is sulfate, one of those is sulfite. Which one is which? Which one is this one?
Sulfite.
sulfite, and this one is sulfate. Okay, how about here? Phosphate or phosphite? Which is which? Which is this one? Phosphite, and this one is phosphate. How about these two? Which one's this one? Chlorite, and this one is chlorate. Okay, does everybody see that? So that is the first pattern, is that when we talk about those oxyanions, a lot of them end in ate and ite. So we could say, I ate one more oxygen. Okay. We'll add to that sentence later. So we'll say, I ate one more oxygen. Okay, I ate one more oxygen. So eights have one more oxygen than ites. So now you only need to know half that, right? Eights have one more oxygen than ites. But the problem comes in, we do have to know this exact formula as well as the charges. Okay, wow. So, that's where it gets confusing. Sulfate has 4 oxygens, nitrate has 3. And then we're thinking, well, why does some chloride has 2, but sulfite has 3, and those are all a little bit different, aren't they? And the charges, wow, some are -1, some are 2, -3. They're just all over the map. Man, that's difficult. Okay, so what we want to do is simplify that, and that's what we're going to tie to the periodic table. So that's where we're going to use our patterns to the periodic table. So when you are memorizing your polyatomic ions, remember about the ate and ite. That's our first pattern. And then when we come back on Monday, we'll use this, we'll talk about this, to put more patterns to the charges so that you could remember all the charges. But in the meantime, work on those polyatomic ions, make flashcards, write them out, practice that, okay, because we need to get these down. Does that make sense?
I was going to do this one, I am one oxygen light.
I am one oxygen light. Yeah, you can say that's another one. I am one oxygen light. Okay, that's a cute way to say that. All right, is everybody okay? We're going to practice and study those polyatomic ions, right? Okay, good job, everyone. Woo, good job. Okay, we will see you back on Monday. Work on those polyatomic ions. We got a lot of days in between. We don't want to forget stuff. Practice, practice. Work on polyatomic ions. Good job.